Good day, class. In the previous videos, we learned how to differentiate the form f to the g, or function raised to another function. One possible method is through logarithmic differentiation, the first topic of this lecture. Now in this last video, we will be studying the derivatives of other classes of functions, namely the inverse circular, hyperbolic, and the inverse hyperbolic functions. Now without further ado, let us begin. So we have the following theorem that indicates the derivatives of the inverse circular functions. Let's try to read them one by one and try to find out if there is some sort of pattern. The derivative of the inverse sine function will be 1 over square root of 1 minus x squared, very much similar to the derivative of the inverse cosine function, where we only append a negative symbol for the derivative. For tangent inverse, we have 1 over 1 plus x squared, and the negative for cotangent inverse, and the derivative of secant inverse will be 1 over x square root of x squared minus 1, and the negative for cosecant inverse. Essentially, the first pattern that we need will be that if it starts with the letter c, then the derivative will be negative. Very much similar to the circular functions. Also, we only need to memorize three forms: the 1 over square root of 1 minus x squared, the 1 over 1 plus x squared, and the 1 over x square root of x squared minus 1. Now, something very peculiar about these formulas is the following. Remember, when we deal with the derivative, for example, of the power function x to the n, the derivative is also a power function. And the derivative of a circular function is still a circular function. The derivative of an exponential function is an exponential function as well. However, when dealing with this inverse circular function, it turns out that it has some similarity with the derivative of the logarithmic function, and that is, the derivative is not its own. When you get the derivative of these functions, you will obtain a quantity that is of course not an inverse circular function. In this case, it's an algebraic expression that has a square and some part of the derivative. That is something that is common for all of this. As you see, you have an x squared in all of these quantities. Now, a good question is, how is it that from the derivative of an inverse circular function, we obtain the following? Now, let's try to prove the following statement, number 1, and the rest will be proved similarly. Now, for example, I have y equal to sine inverse x, and I want to find dy over dx. Now, since I do not know the derivative of sine inverse, what I'll do is I'll use the property that if y is equal to sine inverse x, then sine y is equal to x. And this is good because I know the derivative of sine function. Namely, if I differentiate both sides implicitly with respect to x, I'll have 1, which is the derivative of the left hand side, equal to the derivative of the right hand side, which is just cosine y, of course multiplied by dy over dx, thus giving me that dy over dx is equal to 1 over cosine y. This as an expression will be great. However, what we want is a derivative whose dependency with y that does not have any dependency with y and only is dependent on x. So what I'll do is I will try to express cosine y in terms of x. Fortunately for us, I already know that x is equal to sine y. So I can express this in terms of x as long as I can express it in terms of sine. So what is the relationship between sine and cosine? Well, that is the Pythagorean identity. And that is sine squared plus cosine squared equal to 1. Solving for cosine y, I'll obtain plus minus square root of 1 minus sine squared y, which in itself is somewhat great. However, the presence of the plus minus will actually be a problem for us. The good thing, and this is the main trick here, is that when we try to find the inverse of your sine function, we restricted the domain so that it will become 1 to 1, and the restriction will be from negative pi over 2 to pi over 2. There's a reason why we did it like this, because remember, this values will actually occupy the fourth quadrant to the first quadrant, and in both of those quadrants, cosine y will always be non-negative, and that will tell me that I can choose the plus in this plus minus, giving me the formula that I want, 1 over square root of 1 minus x squared. In terms of the proof, this uses some technique which we call the inverse function theorem, and by the restriction that we implied, that we gave for sine, I will be able to get this formula. It's also important to know that we have a restriction for secant and cosecant inverse, and the reason why we did the restriction, if you still remember it, is because we want to have the same formula. You will see here that if you change the restriction, for example in here, then you're not sure if you're going to get plus or minus. For example, if you restricted sine for pi over 2 to 3 pi over 2, instead of choosing the plus, I should actually choose the minus. But anyway, if we stick with our definitions for inverse circular function, at least I am sure that the formulas that we have will all hold, from sine to cosecant inverse. Let's try to find dy over dx involving these expressions. Now, what makes it a little bit complicated is the action. Just like the ln that you express it, the argument as a reciprocal or put it in the denominator. For inverse circular functions, we do the same, and that is the derivative of sine inverse x, whatever the x here is, will be placed in this expression x squared. So for example, the derivative of y equal to sine inverse 3x will just be, I'll express it as 1 over square root of 1 minus whatever the argument is, 3x to square, and of course, you multiply it with the derivative of whatever is the argument or whatever you placed inside, and that is a 3, giving you the final answer of 3 over square root of 1 minus 9x squared. So it's a matter of following the formula or knowing the formula, as well as to substitute whatever the argument is to the expression that we have. For example, I have cotangent inverse ln x. Since a cotangent starts with the letter c, then the derivative will be negative. Dy over dx will be negative of 1 over 1 plus x squared. I'll replace x with ln x since it's the argument, and you multiply it with the derivative of ln, which is 1 over x. As a topic, it's not really that hard. You just need to first memorize the formula and know where to place the x. In this case, you normally place the x somewhere in the denominator. Now let's have one last example for the derivatives of inverse circular functions. I have this equation and see that I cannot express y explicitly in terms of x. So I'll be implicitly differentiating this. So I will differentiate first the left-hand side. Notice you have a base and an exponent. As you have learned before, you will check what the constant part is. Since 1/5 is a constant, I'll use the exponential rule. And the derivative will be, I'll copy 1 to the 5th y, ln of the base, times whatever is the derivative of your exponent. In this case, that will be dy over dx. Of course, I next differentiate log of x minus y to the base 2. The base is a constant, greater than 0, not equal to 1. I can use the formula for the logarithm that will become 1 over the argument x minus y, ln of my base, which is 2. Of course, I will multiply this by the derivative of my argument, which in this case will be 1 minus dy over dx. Don't forget, we need to have a grouping symbol here. Now let's differentiate the last part, and this is actually one of the tricky parts. There are two main mistakes or common mistakes when you deal with derivatives of inverse circular functions. The first one is the notation. Notice that whenever you have a negative one negative one as your exponent or as a form cosecant to the negative one, the negative one is actually an indicator of being an inverse and not an exponent. That means you don't use power rule here. You can see here that you have a square of the cosecant inverse to indicate that whenever there is a power for an inverse function, you will actually need to write it outside. So in this case, the derivative will be first the derivative of the square, which is 2 times the inverse of your cosecant 3x squared times the derivative of what is squared, in this case cosecant inverse. Again, the negative one here is not an exponent. So the second probable mistake for this topic will be for secant and cosecant. Unlike for sine to cotangent inverse, there are two x's in the denominator for secant, for the derivative of secant and the derivative of cosecant inverse. So that means the 3x squared here will actually go in two parts. So you still have a negative, and you have a 1 over 3x squared, square root of the square of this, which is 9x to the fourth minus 1. And of course, you cap it off with the derivative of 3x squared, which is just 6x. Of course, we end this by solving for dy over dx, and this is just a simple application of what you learned in implicit differentiation, so I will just write down the answer here, which is just given as follows. The important part of this topic is to memorize the formulas. Number 2, to note to yourself that the notation is a little bit problematic, so you need to know that the negative one is not an exponent. It's a very important thing. And how the action behaves, or the derivative of a sign, you will have the argument to be placed inside the x squared in the denominator, and for secant and cosecant, you have two x's where you need to evaluate your argument. And that is for the derivatives of inverse circular functions. Now let's go to our next class of functions, which is the hyperbolic functions. Now the good thing about the hyperbolic functions is that the formulas are almost the same as the circular. For example, the derivative of the hyperbolic sine of x will be hyperbolic cosine of x. The derivative of hyperbolic cosine will be sine, and then the following will follow. Now there are two main differences between the derivatives of the circular and the derivative of the hyperbolic. Because if you notice, the pattern will be very much similar. Sine is to cosine, tangent to be sec squared, and sec will be sec tang. However, of course, all of the quantities here will have an h because you're dealing with hyperbolic functions. So the hyperbolic sine will have hyperbolic cosine. You have an h on both ends. And last but not the least, that you have a difference in the sign. Before, in the derivatives of circular functions, our motto is that if it starts with c, the derivative is negative. But for the hyperbolic functions, the motto will be as long as it is part of SOHCAHTOA, it is positive. Otherwise, it is negative. So the derivative of sine, cos, and tang will all be positive. Everything else will be negative. In terms of changes, there is a change with the sign for the derivative of cos, and the change in the sign for the derivative of sec. So this should have been negative if it is circular, and this should have been positive if it is circular. But in this case, you have plus, 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 minus, minus, minus. The proof of this is very easy. It's just a matter of expressing your hyperbolic function in terms of its exponential form. For example, sinh of x is just e to the x minus e to the negative x over 2. If you differentiate this, what you'll get will be the following. Remember, the over 2 is just a constant, so it's still over 2. The derivative of e to the x will be e to the x, while the derivative of e to the negative x will have a negative 1 after chain rule, thus giving me e to the x plus e to the negative x over 2, which is exactly the hyperbolic cosine of x. Now, in terms of formula, at least we don't need to memorize much. Just need to memorize the formula or the pattern for the sign. For example, I want to differentiate y equal to hyperbolic cosecant of x to the fifth minus 2. Same thing. Remember the notes that we have in the derivatives of the circular function. We have two x's for sech and cosech. So that means the derivative will be negative of cosech cos, where the argument will be exactly x to the fifth minus 2, x to the fifth minus 2. The next in line will be the derivative of x to the fifth minus 2, and that's just 5x to the fourth. So the things that you have learned in your derivatives for circular function will still be noted here. Just remember the sign and the h's. We also have the same technique or same logic whenever we deal with powers, because similar to the circular functions, the hyperbolic function powers will actually occur after the function itself. For example, if I want to get the derivative of tanh cube of square root of x plus 3, the first or the outermost operation in applying chain rule here would be the cube. So I'll have first 3 tanh squared of square root of x plus 3. The next in line will be tanh, which in this case is positive sech squared. Whatever the x is, in this case square root of x plus 3. And then I differentiate square root of x plus 3, which gives me 1 over 2 square root of x plus 3. Of course, you still multiply this by the derivative of x plus 3, but that is just 1 and you can just omit it. Now let's have one last example, which is y equal to cos x to the sinh x. Cos x here should be assumed to be positive. Now, two things to note here is that the first, that the quantity that I wish to differentiate is of the form function to the function, and you can refer to the left hand side on which technique to use. The second thing to note here is that the assumption that cos x is positive is actually not needed, for the reason that whatever the x is, the hyperbolic cosine of x will actually not only be positive, but is always greater than or equal to 1. Nonetheless, to get the derivative, I will choose either logarithmic differentiation or to express that as e to the g, l, and f. I will choose the latter, which is I will express cos x to the sinh x as e to the sinh x ln of the base cos x. Differentiating this, I'll have dy over dx equal to the derivative of the natural exponential function will be to just copy it multiplied by the derivative of the exponent. And just like our expectation, you will have a product rule here, namely the derivative of sinh, which is just cos, times the second plus the first times the derivative of ln cos, and even though it starts with the letter c, I have 1 over cos x times the derivative of cos, which is positive sinh x. And you can further simplify this and you will get the answer. Of course, if you don't simplify it, it's also okay, as we have already tested that you know the formulas for the derivatives of the hyperbolic functions. Now we go to our last class of function, and that's the inverse hyperbolic. The good thing about the hyperbolic functions is that it's very similar to the circular, and it turns out that the inverse hyperbolic function is very similar to the inverse circular functions as well. So how we deal with the derivatives of the inverse circular is how we are going to be dealing with as well for the inverse hyperbolic. The only difference is that we do not have that pattern where if it starts with c, it becomes negative. Actually, each one of these 6 formulas is unique in its own right. For example, the derivative of the hyperbolic sine inverse of x will be x squared of x squared plus 1. For cos inverse, I'll have square root of x squared minus 1. For hyperbolic tanh and cos, they have exactly the same derivative, 1 over 1 minus x squared, but they have different domains. For hyperbolic tanh, that's for the case when the absolute value of x is less than 1, and cos inverse for the case when x is greater than 1. Sech inverse and cosech inverse are both negatives, I have negative 1 over, I have x over square root of 1 minus x squared for such inverse, and 1 over absolute value of square root of x squared plus 1 for cosec inverse. You can view these formulas through our module or through the formula sheet that was given in the backside of standard calculus textbooks. Now, of course, since it's hard to memorize this, the best way to memorize them will be to do a lot of examples. For example, I want to get the derivative of sinh inverse of 1 minus x. Similar to the derivative of inverse circular functions, I just need to evaluate this quantity inside my derivative. So I'll have 1 over square root of, I'll replace x with 1 minus x, and then I differentiate whatever I placed inside, or the 1 minus x, that's a negative 1. In terms of application, we don't have that much difficulty. It's a matter of recognizing what function that you're differentiating and just applying the formula well. If, for example, I want to differentiate this is y equal to cos inverse x to the fourth minus sec inverse of 1/4 to the x. Then it's a matter of applying the rules properly. For example, the outermost operation for number 2 is a difference. So I'll use some rule. I'll get the derivative first of cos inverse, and cos inverse will be 1 over 1 minus x squared. I'll replace x by x to the fourth. I'll have x to the 8th. Of course, by chain rule, I'll have 4x cubed. Minus, for sec inverse, you have a negative. So that means that becomes a plus. I'll replace the x with 1/4 to the x, which will be giving me this 1 over 1/4 x square root of 1 minus 1/4 to the 2x, and then differentiate the argument 1/4 to the x. This is a base, and there's also an exponent. Since the constant part is the base, I'll use exponential rule, and that is 1/4 to the x ln 1/4 times the derivative of the exponent, which is just 1. And that's how you differentiate number 2. Now let's have one last example, which is the derivative of log of cos inverse 2x to the base 10. Of course, this is just a simple application of your chain rule. I'll differentiate the logarithm, and that's just 1 over the argument cos inverse 2x ln of my base. That's the first function. The next will be cos inverse. Now, just like the inverse circular function, you just need to be very careful about your notation here. A very classic mistake is not just forgetting the formula, but because of the similarities of the notations of the circular, the hyperbolic, the inverse circular, and the inverse hyperbolic function, as there's only just a change with the existence of the h or the existence of the negative 1. But this is hyperbolic cosine inverse. Again, if there's a negative 1 in your exponent as circular or hyperbolic, that is automatically treated as an inverse function. If you want the reciprocal, the negative 1 here will not be in this part, but rather outside. So in this case, the derivative of the hyperbolic inverse, hyperbolic cosine inverse, will be 1 over, I'll replace x by 2x, and then multiply by the derivative of 2x, which is just 2. You see here that though we did learn a lot of formulas for this video, in terms of its application, it's not really that problematic. Just remember, for the inverse circular and hyperbolic, be very careful of the notation. As for the derivatives of the hyperbolic function, be careful of the sign. As long as you are careful for these 2 points, you'll be able to get the derivative well, as long as you have memorized the formula well. Now, I hope you learned well in this video. Stay safe, and thank you for watching.